Now that we have looked at how to visualize distance traveled, we will look at a more involved example. We will use again that distance traveled is velocity times time. Let's now look at an example where the velocities of a runner starting a race are given by the following table. At t equals 0, the velocity is 0. After 2 seconds, the runner is traveling at 8 feet per second. After 4 seconds, the runner is traveling at 14 feet per second. And after 6 seconds, the runner is traveling at 18 feet per second. Let's start by finding how far the runner traveled from t equals 0 to t equals 2. That is, how far did they travel in the first 2 seconds? We will use that the distance traveled is velocity times time. But over the first 2 seconds, we don't have a constant velocity. The velocity goes from 0 feet per second to 8 feet per second. So what should we use as our velocity? Well, we will start by using both. We can get an overestimate, that is an estimate which is more than the actual distance traveled, by assuming the runner traveled at 8 feet per second for the entire 2 seconds, for a distance of 8 times 2, which is 16 feet. We can also get an underestimate, that is an estimate which is less than the actual distance traveled, by using our smaller velocity, 0. So the distance traveled is 0 times 2, which is 0 feet. Logic tells us that neither of these are actually correct, and the actual distance traveled is somewhere between 0 and 16 feet. So we have a range of what the distance traveled could be. Let's put this information aside and figure out how far the runner traveled in the next 2 seconds, that is from t equals 2 to t equals 4. Again, over this time interval, the runner is not traveling at a constant velocity. But again, we can get an overestimate and an underestimate. For the overestimate, we will use a velocity of 14 feet per second. So the distance traveled is 14 times 2, or 28 feet. For our underestimate, we will use that the velocity is 8 feet per second. So our underestimate is that the distance traveled is 8 times 2, which is 16 feet. Again, logic tells us that the runner actually traveled somewhere between 16 and 28 feet in those 2 seconds. Let's now find out how far the runner traveled over the last 2 seconds, from t equals 4 to t equals 6. Again, the runner is not traveling at a constant velocity, so we have to get an overestimate and an underestimate. Our overestimate is that the distance traveled is the higher velocity 18 times the 2 seconds we traveled for a total of 36 feet. Our underestimate uses our lower velocity, 14, to get that the distance traveled is 14 times 2, which is 28. Again, these two estimates tell us that the runner traveled somewhere between 28 and 36 feet over the last 2 seconds. We will use this information to figure out how far the runner traveled over the entire 6 seconds. That is, how far the runner traveled from t equals 0 to t equals 6. As we did in each 2-second time interval, we will get an overestimate and an underestimate. For our overestimate, we will use that our runner traveled at most 16 feet in the first 2 seconds, and at most 28 feet in the next 2 seconds, and at most 36 feet in the last 2 seconds. So our runner traveled at most 16 plus 28 plus 36, or 80, feet in the first 6 seconds. Notice that what we did is break down our 6-second time interval into 3 smaller 2-second time intervals and estimated the distance traveled over each of those 2-second time intervals, and then added them up to figure out how far the runner traveled in the entire 6 seconds. We will calculate our underestimate similarly. Using our underestimates, we know that the runner traveled at least 0 feet in the first 2 seconds, and at least 16 feet in the next 2 seconds, and at least 28 feet in the last 2 seconds. So over the entire 6 seconds, the runner traveled at least 0 plus 16 plus 28, or 44, feet. So while we don't know exactly how far the runner traveled, we know that the runner traveled somewhere between 44 and 80 feet. The problem is, this is a pretty big range. So the question becomes, how do we get a better estimate? Or in other words, how do we get a smaller range of possible distances? We will do this by calculating the distances over smaller time intervals. It's worth pointing out that we took this approach of using smaller intervals before with the derivative. Now, we will find how far the runner traveled from t equals 0 to t equals 6, but instead of breaking the 6 seconds up into 2-second time intervals, we will break it up into 1-second time intervals. Notice that this requires more data because we need to know what the velocity is at 1 second, at 3 seconds, and at 5 seconds. But as long as we have this data, we can use this to find our overestimate and underestimate again. Now we will get our overestimate. Remember, on each time interval, we will use our higher velocity so that we can find the most distance our runner could have traveled. Doing our calculation, we get that in the first 1-second time interval, the runner traveled at 4.5 feet per second for 1 second, so 4.5 times 1. In the next time interval, we estimate that the runner traveled 8 feet per second for 1 second, so 8 times 1. Carrying on, in the next time interval, we have that the runner traveled 11 feet per second for 1 second, then 14 feet per second for 1 second, followed by 16.5 feet per second for 1 second, and finally in our last time interval, we use that they traveled at 18 feet per second for 1 second. So over the entire 6-second time interval, they traveled 4.5 feet plus 8 feet plus 11 feet plus 14 feet plus 16.5 feet plus 18 feet for a total of 72 feet. So our overestimate is that the runner traveled at most 72 feet in 6 seconds. Let's now compute our underestimate in a similar fashion, except here, in each time interval, we will use the smaller velocity. Doing this, we get that the runner traveled 0 feet per second for 1 second over the first time interval, 4.5 feet per second for 1 second in the next time interval, followed by 8 feet per second for 1 second, then 11 feet per second for 1 second, 14 feet per second for 1 second, and finally in our last time interval, they traveled at 16.5 feet per second for 1 second. So in total, we estimated that the runner traveled 0 feet in the first time interval, 4.5 feet in the next time interval, 8 feet in the third time interval, then 11 feet in the next time interval, 14 feet in the next, and finally 16.5 feet in the last time interval, for a total of 54 feet. So our underestimate is that the runner traveled at least 54 feet in the 6 seconds. So we can conclude that the runner traveled somewhere between 54 feet and 72 feet in those 6 seconds. Notice that compared to our older estimates that we have a smaller range. Before, we knew the runner traveled somewhere between 44 and 80 feet, but now we know the runner traveled between 54 and 72 feet. So we have a better estimate. So we can conclude that by having smaller intervals, we get a better approximation. But it's worth noting that we also had to do more work, because we had to compute our estimates over 6 time intervals instead of only 3. We will use this idea in future videos to get better and better and better approximations, just as we did with the derivative by taking smaller and smaller time intervals. Before we close, it is worth noting that sometimes we want our approximation to be a number rather than a range of numbers. At this point, the best approximation that we can get is to average the over and under estimates. In this example, we can estimate that our distance traveled is approximately 72 for our over estimate plus 54 for our under estimate over 2, which comes to 63. So our best estimate right now is that the distance traveled was 63 feet.